In the last class, we discussed about few relationships like du is t t ds minus p dv, and from there we got relationships like del u by del s at constant v is t and del u by del v at constant s is minus p. We also found dLh is TdS plus VdP. From there we got del H by del S at constant pressure gives T, and del H by del P at constant S gives V. Then we had del dA is minus p dv minus s dt, and from there we got del a by del v at constant t is minus p, and del a by del t at constant v is minus s, and we had dg is v dp minus s dt, and from there we got del g by del p at constant temperature is volume, and del g by del t at constant pressure gives us minus s. Okay, so these are the relationships we have got so far. Okay, now if we consider the expression del u, we have considered the expression. Now we got del u by del s at constant v is t. From there we get del 2 u by del s del v is del t del v. Okay, we also had del u by del v at constant s is minus p. Okay, from there we can write del 2 u by del v del s is minus del p by del s at constant p. This is at constant s. Okay, since u is a state function, so since u is a state function, it says du is exact differential that we have obtained previously. We can write del t by del v at constant s is minus del p by del s at constant v, right? Okay. Similarly, we can also obtain del T by del P at constant S is del V by del S at constant P. We can also obtain del S by del V at constant temperature is del P by del T at constant volume, and del S by del P at constant temperature is minus del V by del T at constant pressure. So these four equations or expressions are known as Maxwell's relations. Okay. We can have another set of Maxwell's relation. Like del U by del S at constant V is del H by del S as constant P, del U by del V at constant S is del A by del V at constant T, del H by del P at constant S is del G by del P at constant T, and del A by del T constant V is del G by del T at constant P. Okay. So these are another set of Maxwell's relations. Next, we will prove that or show that for ideal gas, del U by del V at constant temperature is 0. Okay, so for isothermal process, okay, we know that for ideal gas there is no change in internal energy. If temperature does not change, then internal energy will not change. Okay. So let's see whether we can prove it or here. Okay, so prove. We know du is Tds minus Pdv, right? Again, S is a function of T and V, right? We know S function of temperature and volume, so we get ds is del S by del T at constant volume dt plus del S by del V at constant temperature dV. So if you substitute the value of T ds in equation 1, so we get, substituting the value of ds in equation 1, we get du is T del S by del T at constant volume times dt plus T del S by del V at constant temperature times dV minus Pdv. Okay, and we can rearrange this like T del S by del T at constant volume dt plus T del S by del V at constant temperature minus P times dV, right. Suppose this is our equation 2. again U is function of T and V, right? So internal energy is function of temperature and volume. So we can write du is del U by del T at constant volume times dt plus del U by del V at constant temperature dV. And this is our equation 3. Now, if we equate or equating the coefficients of dV in equations 2 and 3, we get T del S by del V at constant temperature minus P is del U by del V at constant temperature. Okay, now from Maxwell's relations we know del S by del V is nothing but dP by del P by del T at constant volume minus P. Now, for ideal gas, P is nRT by V, we know. So, del P by del T at constant volume gives okay, nR by V. So, we can write T times nR by V minus P is del U by del V at constant temperature. Okay. So, we can write del U by del V at constant temperature is 0, right. Okay. So, now we have proved that for ideal gas del U by del V at constant temperature equals to 0. Okay. So, next we will prove the change in internal energy as we change the pressure at constant temperature will again 0 for ideal gas. Okay. So, we will prove proof is very similar. Okay. So, here we will consider H or enthalpy instead of internal energy. So, H we know nothing but U plus PV, right. Okay, and for ideal gas PV is nothing but nRT. So, we get U plus nRT. So, for ideal gas PV is nothing but nRT. So, we can write U is nothing but H minus nRT, and this gives you del U by del P at constant temperature is nothing but del H by del P at constant temperature for ideal gas, right. And minus we have one more term here del nRT. You can, if you want, you can write this. Now we know dH is TdS plus ddt. Okay. So, we can write del H by del P at constant temperature. Okay, del H by del P at constant temperature is T del S by del P at constant temperature plus V, right. So, we can write del H by del P at constant temperature is nothing but V minus T del V by del T at constant pressure. Okay. Again we are using here Maxwell's relation. Okay. So, we know V for ideal gas V is nRT by P. Okay. So, here so we can write del V by del T at constant pressure is nR by P. Okay. So, if we go back and check, okay, so del U, so we had del U by del P, we had del U by del P at constant temperature equals to del H by del P at constant temperature minus del N RT by dP at constant temperature. Okay. So, if we substitute the above expressions here, we get del H by del P at constant temperature equals to 0. So, you get del U by del P at constant temperature is 0. Okay. So, this is how one can prove that for ideal gas del U by del P at constant temperature is 0. Next, we know that del G, if you go back and check, we have the expression del G by del P at constant temperature is volume. Okay. Okay, del G, we have del G, we have del G by del P at constant temperature is volume. Okay, is volume. So, we get dG is VdP at constant temperature. For ideal gas, V is nothing but nRT by P. Right. So, we can write dG is nRT by P times dP. Okay. Now, if you do the integration from G1 to G2, pressure is changes from P1 to P2, we get G2 T comma P2 minus G1 T comma P1, okay, is in R T ln P2 by P1. So, if you divide both sides by number of moles, so we get this G by N, if we divide Gibbs free energy by number of moles, we get molar Gibbs free energy, or you can write G2 bar where G2 bar and G1 bar are molar gives free energy. Okay. So, gives free energy per mole is also called chemical potential, you know. So, you can write mu 2 minus mu 1 is RT ln P2 by P1. Okay. So, where mu refers to chemical potential. If suppose P1 equals to 1 atmosphere and P2 equals to P atmosphere. Okay, then we can write, then in that case mu 2 is nothing but mu T and P, and mu 1 naught, mu 1 equals to mu naught temperature. This is standard chemical potential. So, this is known as standard chemical potential. Okay, so we can write from there, we can write basically mu T P is nothing but mu naught T plus RT ln P. So, what is the definition of standard state then? Standard state means pressure is 1 atmospheric pressure and temperature can be anything. Okay, we need to define temperature. Next we will consider, we will discuss Gibbs Helmholtz equation. Okay, so we know G is H minus Ts. So, we can write, we divide G both sides by T. If we divide both sides by T, we get this. G by T equals to H by T minus S. Now, 1 by T del H by del T at constant pressure is nothing but del S by del T at constant pressure. So, we can write D G by T delta T is minus H by T to the 2. Okay. So, this is Gibbs-Helmholtz equation. This is known as Gibbs-Helmholtz equation. Or we can write, similarly we can write d del G by T del T at constant pressure is minus del H by T to the 2. So, this is also another form of Gibbs-Helmholtz equation. So, now we discuss Gibbs-Helmholtz equation. Next. Okay, so next we will discuss one interesting thing, the chemical potential of a pure substance in two phases in equilibrium are equal. Next, we will discuss the chemical potentials of a pure substance in two phases in equilibrium are equal. We will prove it. We know this statement. Okay. Today, we are going to prove it. Okay. So, let us consider system of two phases of a pure substance in equilibrium with each other. Okay. For example, we can consider water vapor is in equilibrium with each other at constant temperature and pressure. Okay. So, we consider we have here you have liquid water and you have water vapor, and they are in equilibrium with each other at constant T and P. Okay. Now, suppose GL and GV represent Gibbs free energy in liquid and vapor states respectively. Okay. Now, we consider that GL and GV, they represent Gibbs free energy in liquid and vapor states respectively. Okay. So, what is the total Gibbs free energy of the system? The total we say G is nothing but GL plus GV, right. So, we can write, so we know G is function of Tp and N. Okay. So, here, so we can write dG is del G by del NL, okay, at constant pressure and temperature times T N L plus del GV del GL here del GV by del NV at constant pressure temperature times dNV, okay, where dNL represents change in number of moles in the liquid state. So liquid and vapor, they are in equilibrium with each other. The sum of the molecules in the liquid state goes to vapor space, go to vapor states, right? And similarly, some vapor molecules in the vapor state comes back to the liquid state. Okay. So, and dNV represents change in number of moles in the vapor state. So, as I stated just now, that some of the molecules in the liquid state go into the vapor state, and some of the molecules in the vapor state come to liquid state. Okay, and since the system is in equilibrium, we can write, okay, or it is quite obvious. It is obvious that dNL is nothing but minus dNV, right? Because the system is in equilibrium. If the system is in equilibrium, or two states are in equilibrium with each other. Okay. So, two states are in equilibrium with each other. So, if you use this condition in equation 1, okay, we write dG is so, if we substitute dNL by minus dNV, we get like this. This and then we get this one Now what is now del G L by dn L is nothing but mu L, and okay, so we get del G L by del N L at constant pressure temperature is mu L, and del G V by del N V is mu V. So we can write dg is mu L minus mu V times dn L. Okay, since at equilibrium dg at constant temperature pressure is 0, we can write mu L minus mu V, mu L minus mu V times dn L is 0. Now, since dn L is not 0, okay, as mentioned earlier that some of the molecules, so from liquid state goes to vapor state. Okay, so dn L change in number of moles in liquid state is not 0. So we can write mu L equals to mu V. Okay, or in other state, other words, chemical potential at or chemical potential in liquid state, chemical potential in liquid state equals to chemical potential in vapor state. Now, so we obtain that dg is mu L minus mu vapor times dn L, right? Okay. For or when or if the two states are not in equilibrium with each other, a spontaneous transfer of matter from one phase to the other will occur in the direction such that dg Tp is less than 0. So, for spontaneous change dg Tp less than 0, that we know. Okay. Now, if dn L is positive, okay, then in order to make dg negative, mu L has to be less than mu V. Okay. So, when chemical potential of liquid state is lower than the chemical potential of the vapor state, then few of the vapor molecules will condense to the liquid state. Okay. On the other hand, if D and L is negative, so it says to make Dg negative, Dg at constant temperature and pressure, mu L has to be greater than mu V. So, when chemical potential of the liquid state is greater than the chemical potential of the vapor state, then some of the molecules in the liquid state will go to the vapor state. Okay. So, we know next we will discuss temperature dependence of chemical potential. So, we know del mu by del T at constant pressure is minus S, right. How did you get that? Or minus Sm, means entropy or molar entropy, entropy per mole. Okay. How did you get it? We know del G by del T at constant pressure is minus S. Okay. So, we can write this one as del G by N by del T constant pressure is minus S by N, and this is nothing but del mu by del T minus S by N. So, this we know, and from there we already discussed this thing in one of the previous classes. If we plot mu versus T at constant pressure, we get like this. Oops. We get like this, this, this. Okay. So, this is known as melting temperature or freezing temperature, Tm. This is boiling temperature or Tb. This is freezing temperature Tf, and this is boiling temperature Tb. So, here solid stable, here liquid stable, and here gas stable. This is the freezing point and this is the boiling point, right. Why we get different slope? We get different slope because entropy, absolute entropy for gaseous state is greater than that of liquid state, than that of solid state. Okay. Okay, since this is there, so we get different slope. different slopes. And the steepest slope we observe for gaseous state. Okay. Now, what would happen if we consider pressure is changed, or pressure is being changed? Okay. So, we will consider now pressure dependence, boiling and freezing point. We know if we change the pressure, boiling point and freezing point changes, right? Both of them they change. Okay. So, how do they change? Okay, let us see. Okay, we know del mu by del P at constant temperature is V bar, okay, or molar volume, or Vm, molar volume. So, how did we get this? We know del G by del P at constant temperature is V, and if we differentiate G versus G by N, okay, so we get this. So, we can write V bar, okay, or Vm. So, how this is how we arrived at this expression here. Now, in general, this is always true that molar volume of gaseous state is much higher than molar volume of liquid state, which is greater than molar volume of solid state. So, this is in general. This is reverse in case of water, that molar volume of ice is lower than the molar volume of liquid water. Okay. But in general, for most of the matter, molar volume of gaseous state is much higher than the molar volume of liquid, which is higher than the molar volume of solid state. Okay. Now, we consider and all these all of them are positive quantities, right? Are positive quantity, right? If that is the case, so if we plot, or if we increase the pressure, or the plot of mu versus P will give you positive slope, right? At a fixed temperature. Okay, if we fix the temperature and if we change the pressure, okay, the chemical potential will increase. Okay. Now, if we plot like this is very important plot. Okay. Okay, so here you have low pressure, here high pressure. Okay. Okay, so at a fixed temperature here, if we consider at fixed temperature here, if we increase pressure, mu increases. Okay. Here also this is, now this is our, consider this point. This is our freezing temperature at a particular pressure, low pressure. If we increase pressure, we get freezing point is this at high pressure value. Okay. Now, what about here? So, you consider this state. Okay. So, this is TB boiling point at a particular temperature this, and at a different pressure the value is this. Okay, TB prime. Okay. So, delta TF is nothing but say TF prime minus TF is much lower than delta TB, that is TB prime minus TB, right. Okay. So, why this is like this? Why delta TF is less than delta TB? Because of value of molar volumes. Okay. So, since molar volume of vapor state is much higher than molar volume of solid state. Okay. So, we get this means delta TF is much lower than delta TB. Okay. Thank you.